Tesla has broken ground on a research chip fab in Austin, while public filings outline a much larger production campus in Grimes County. Give it ASML scanners, applied materials chambers, and KLA inspectors. Is that a fab? Not yet. Together, those tools can process and inspect silicon. They cannot print yield, and yield is the real product of every chip factory. Here is the answer up front. Yes, Musk can build a research fab. With Intel and the equipment industry, he may build a narrow production line for his own chips. But a fast, independent replacement for TSMC or Samsung? No, not on the timetable in the headlines. First, separate two projects that are often blurred together. In Austin, Tesla says a roughly $3 billion development fab is under construction, sized for only a few thousand wafer starts per month. 90 miles away in Grimes County sits the production ambition. Public filings plan about $16.8 billion for Phase 1, spread across 2026 to 2028. 4 proposed phases stretch to 2036 and reach roughly $119 billion only if every phase is completed. SpaceX describes more than 100 million square feet of planned manufacturing space and at least 3,000 jobs. That does not mean 100 million square feet of cleanroom. The campus is planned to make logic, memory, masks, packages, and tested chips. That is a serious industrial plan. It is not yet a demonstrated manufacturing process. Money can buy the visible fab first. A vibration-controlled shell, enormous electrical feeds, specialty gases, vacuum, ultra-pure water, and temperature stability measured obsessively. Much of the factory is actually the utility maze hidden above and below the cleanroom. Then come thousands of tools. Deposition chambers add films a few atoms at a time. Lithography prints a pattern. Etch removes it. Cleaning attacks particles smaller than a virus. Metrology decides whether any of it worked. Terafab has 2 unusual advantages here. It has captive demand from Tesla vehicles and robots, plus SpaceX computing systems. And it does not need to serve every customer on Earth on day one. A research line can narrow the product, accept low volume, and let chip design change with the process. That makes the Austin fab credible, but it delivers only the first payoff, a place to learn. A tool list is not a process. It is hardware waiting for one. If you want the semiconductor story beneath the headline, subscribe. The hardware also destroys the idea of independence. Terafab plans to use Intel's 14A process, a technology Intel itself is still developing. A process is more than a node name. It includes design rules, hundreds of recipes, qualified materials, and control limits that must transfer together. ASML says its own capacity planning now includes expected terafab demand. Musk's team has reportedly contacted Applied Materials, Lam Research, Tokyo Electron, and Samsung for help. That is exactly what a real fab project should do. It also reveals the paradox. The more credible terafab becomes, the more it looks like a new customer of the existing semiconductor supply chain. An ASML scanner does not arrive with a competitive process sealed inside it. A deposition chamber must match the film, mask, etch, clean, and inspection steps before and after it. Move one temperature, one gas flow, or one chamber clean cycle, and the defect pattern can change somewhere else. Even the grand promise of logic, memory, and advanced packaging under one roof joins 3 manufacturing cultures with different materials, contamination rules, and yield models. The machines are individual instruments. A fab appears only when they play one repeatable process. Then the real manufacturing problem begins: yield. Imagine the first wafer comes back with thousands of bad dyes. A KLA inspection system finds a repeating defect near one edge. Was it the mask? A drifting etch chamber? A particle in a robot? Film stress from a deposition recipe 2 days earlier? Engineers classify the defect, correlate tool histories, change one variable, and run another lot. The new recipe fixes the edge but creates a failure in a later metal layer. So the loop turns again. Inspection, diagnosis, recipe, wafer. Inspection, diagnosis, recipe, wafer. That loop is the learning machine. The same model of tools can produce very different economics in two fabs because one organization closes that loop faster. Every good die recovered from the edge lowers unit cost. Every hidden failure burns another expensive cycle. TSMC says a new fab normally takes 2 to 3 years to build, then another 1 to 2 years to ramp. Intel currently targets high-volume 14A manufacturing in 2028. That does not make Terafab impossible. It means a 2026 to 2028 construction plan cannot also be evidence of mature yield. Buildings follow schedules. Yield follows data. And the learning loop does not live inside machines. It lives across people. Process integration, yield engineering, masks, metrology, contamination control, facilities, software, and the field service teams from every equipment supplier. These teams must solve problems together, around the clock, without contaminating the next experiment. The rarest fab asset is often the engineer who recognizes which invisible variable moved at 3 in the morning. Tesla can hire experts. Its job listings already point toward gate-all-around logic, high-bandwidth memory, lithography, and advanced etch. That proves direction, not capability. The company does bring real strengths: capital, urgency, vertical integration, and a captive buyer willing to redesign the chip around manufacturing limits. Those advantages can shorten the business case. They cannot shorten the physics. SpaceX's own prospectus says substantial compute hardware would still come from outside suppliers, even if Terafab succeeds. That is not a weakness. It is the credible model. Internal learning, Intel process support, global tools, and outside capacity working together. So the credible path is a staircase, not a leap. First, use Austin to learn on small lots. Second, qualify one narrow captive chip or packaging flow with Intel and the toolmakers. Third, transfer only what is stable into Grimes County. Then expand if the yield curve earns the next phase. That path could create a valuable production fab. It does not require replacing TSMC, Samsung, or Micron, and it does not prove the 1 terawatt ambition will arrive. That figure describes a long-term company target for annual compute hardware, not the plant's electricity draw or current output. Can Elon build a chip fab? He can build the land, shell, utilities, and tool fleet. He may build a useful captive process with years of partnership. But the full terafab becomes real only when repeated wafers produce repeated good dies at a competitive cost. Money can build the cleanroom. Only learning can build the fab. To see who actually builds the machines inside that cleanroom, watch Applied Materials versus Tokyo Electron next.